All right, welcome everybody. Today we are going to talk about Calc Lesson number 16, and this is our first day of section 2.4, which is about something called the chain rule. Now, just to set the scene here a little bit, we are still going to be taking derivatives for the rest of the chapter, but here in section 2.4, we're going to learn how to do so a little bit more efficiently, again, with something called the chain rule, and we are going to cover the chain rule over several days, so today is really just the introduction. Before we even get to that, I want you to consider the following, which would be find the derivative of, and then let's say you had 3x squared plus 2x squared. Now, you might be looking at this and thinking to yourself, well, yeah, that kind of looks similar to the problems we've been doing so far. What's the big deal? Well, that's true, and it's also not true. If there was a question like this that you've seen so far, you were not allowed to take the derivative in its current form. The chain rule will allow you to take the derivative in its current form, but before we get into that, let's review what we would be able to do so far. So you don't have to write down these first two slides unless you really want to. I'll let you know when you should start writing it down. So option number one for how you would solve the problem in question would be to multiply out, which would mean to FOIL out 3x squared plus 2x squared, and then use the sum and difference rules to take the derivative. So 3x squared plus 2x squared, you would go ahead and start by rewriting that as two different copies. Then you would, of course, use the magic word FOIL, first, outers, inners, last. Your outers and your inners would both be 6x cubed, which you would then combine to get 12x cubed. And then if you were to use the power rule one term at a time, you would bring down the exponent, multiply it by whatever's in the front, and then go to the one less power. And you could say without a doubt that the derivative f prime would be equal to 36x cubed plus 36x squared plus 8x. Now, yes, we have seen problems like this before, but again, you weren't allowed to take the derivative in the form that the problem was given, so you did have to do a little bit of extra work. And again, the chain rule is going to allow us to be a little bit more efficient. That's option one, and turns out there's actually a second option for how we know how to do this problem, and that's to use the product rule. So again, if you were going to use the product rule, you would start by rewriting 3x squared plus 2x as two different copies, both of which would be the same. The product rule would say, take the first times the derivative of the second plus the second times the derivative of the first, and you notice you're getting the same values because 3x squared plus 2x would be both the f and the g, and therefore the f prime and the g prime would be the same. If you were then to FOIL out each of these quantities, you would of course get the same four terms each time. If you combined all the like terms, you are still going to get 36x cubed plus 36x squared plus 8x. So, of course, the two methods so far, product rule and then multiplying it out, you do in fact get the same answer. And now on the next slide, you should start writing it down. It's your third option. It's actually the best option, and that is using the chain rule. So let's go ahead and take a look at the All right, so using the chain rule, here is what you are going to do. You are going to be able to take the derivative immediately. In order to take the derivative using the chain rule, you're going to take whatever the exponent is, you are going to move it to the front, you're going to take the entire quantity, 3x squared plus 2x, you're going to raise it to the one less power, which 1 less than 2 would be 1. Then you have to multiply by the derivative of the inside. So you now have to multiply by the derivative of 3x squared plus 2x. So the derivative of 3x squared would be 6x. The derivative of plus 2x would be plus 2. And that, in a nutshell, is what the chain rule is. You apply the rule that you already know, which was the power rule. We've done that literally hundreds of times, but we've actually never done it for a problem that had this more complicated inside. If you were to go back and look at all the problems that we never did ones like that because you weren't allowed to. You have to do these more complicated problems by then multiplying by the derivative of the inside. And again, that's called the chain rule. So where would you go from here? Well, from here, I'm going to take this 2 and I'm going to distribute it inside. So that's going to give me 6x squared plus 4x times 6x plus 2. I'm going to FOIL that. So 36x cubed plus 12x squared plus 24x squared plus 8x. And yes, this should be super familiar at this point. The derivative is still 36x cubed plus 36x squared plus 8x, which is, of course, the same answer that you got the previous two ways. Now, let's be honest. In this case, perhaps this didn't really look or feel much more efficient than the first two rounds, but I want you to consider, what if this had been an exponent of 4 or 10? You certainly would not want to sit there and multiply out 10 copies of something, and you certainly wouldn't want to then have to take all those derivatives. So as this exponent gets larger, the chain rule gets more and more efficient. Consider not just large exponents, but consider fractional exponents like a half or negative 2/3. There's really no easy way to take derivatives that we know so far using those weird exponents. So it turns out that the chain rule is going to be the only way to go about that. So now, again, we're going to start kind of defining the chain rule. So first some words and then also some notation. So when do you use the chain rule? Well, you're going to use the chain rule for composite functions. So hopefully you remember that a composite function is basically an f of g of x, or there could be more than two functions in a row. The thing that's kind of interesting about when you go to take derivatives using the chain rule is you're actually going to work from the outside in. Normally, whenever we do anything with composition, you're working from the inside out. So that is going to be a little bit new. But again, the main way that you know that you have to use the chain rule is when you have a composite function. So let's go ahead and review what would it be to be a composite function. So let's take a look at the left-hand column. These are examples of problems where you would not have to use the chain rule compared to the right-hand side where you would have to use the chain rule. And again, you're going to have to use the chain rule in the second column if something could be made using a composite. So if you look over on the left side in the first row, you have x squared plus 1. So x squared plus 1, that's a simple function. You could technically write it as to the first, but as long as you can write it only to the first, then you wouldn't do that. Compare that to the one on the right, you would write this as x squared plus 1 to the 1/2, which means you would have an inside function of x squared plus 1. You'd have an outside function of something being raised to a half. So a more complicated problem with a more complicated exponent, that's where you have to use the chain rule. Consider the next row. You just have a simple sine of x. Compare that to the sine of 6x. That means you put some function, 6x, into the sine function. Because that's a composite function, more complicated, you need the chain rule. A simple 3x plus 2 compared to a 3x plus 2 to the fifth. Again, that more complicated exponent and that more complicated inside is a chain rule. In the last row here, the x would be fine, but if you look at the tan x compared to the tan of x squared, the fact that you're taking the tangent of something other than just a single variable, that's how you know that you're going to have to bring the chain rule in. So as we work through section 2.4, you'll kind of start recognizing when you do and don't have to use the chain rule. Just be clear that from this point forward, you don't have to use the chain rule for every problem. We're going to use them for most of them, of course, but just make sure you know that you don't have to use it. It's just always now an option. So if we're going to define the chain rule, let's go ahead and do so on this slide. So bring back up my highlighter here. So there's a couple of different ways that you can describe the chain rule. There are two different sets of notation, and then I'm going to kind of summarize it for you on the next screen. So as you start copying it down, which I think you should, I'm going to go ahead and talk through it a little bit, and then your teacher, I'm sure, will pause it to give you extra time. So the first two statements are really just qualifiers here. If y equals f of u is a differentiable function of u, and u equals g of x is a differentiable function of x. Now, those are just qualifiers that have to be true. We're not going to try to trick you or anything and make them not true, but it is important you know that they have to be a thing. Then, if you take some composite, y equals f of g of x, and again, based on what the definition says, they're assuming that u is the g of x, which is the inside function, and f of u is the outside function, which is the y equals. So if you have two differentiable functions and you make y equals f of g of x, then you can say that the derivative of y in terms of x, which is dy over dx, is equal to the derivative of y with respect to u times the derivative of u with respect to x. So we did try to warn you that there would come a time when using this d notation would be more important than just using y prime. That time has arrived. So from this point forward, whenever your function is y equals, you should use dy dx as opposed to using y prime. And again, if you look at what's going on here, when they say take dy du, they're assuming you're doing that because they're assuming that you're taking the derivative of the outside function. Then they're assuming you're taking the derivative of the inside function. So again, work from the outside in. If you don't really happen to like that notation with u's and x's, here is an equivalent way of saying it. If you're taking the derivative in terms of x of some composition f of g, you're going to start by taking the derivative of the composite f of g. You would then have to multiply by the derivative of the inside function, which would be g prime of x. Sorry, I was trying to change the color there, but it wasn't really working. So let me just bring back my pen here. To change that in a second. But again, if you're taking the derivative of some composition, you would have to take the derivative of the outside function, and then you'd have to multiply it times the derivative of the inside function. So there is quite a bit of notation there. Again, your teacher will pause it to give you a chance to catch up, and then we're going to kind of summarize it on the next screen, and then of course see it in action. So in plain language, here it is what you're trying to do. You are trying to say that the chain rule means the derivative of the outer function times the derivative of the inner function. So whether you think of it as an f of g or an f of u doesn't really matter for now. If you're thinking of it as an f of g, then your f is your outside function. If you're thinking of it as an f of u, then f is still your outside function. Whereas if you're thinking it of f of g versus f of u, your g and your u would both be your inner functions. So the f would be the outer function, and then either g of x or u would be the inner function, again, depending on which of these two things you wanted to use. Using the u, it's not such a big deal right now. It becomes a huge deal the second half of the year when we start integrating, but for now, again, either one will be fine. So I think the best way to make sure that we know what's going on is to go ahead and do some problems. But before we do some problems, we first have to make sure that we understand how do we know who's the inner function and how do we know who's the outer function. So in order to do that, we have to remember what decomposition is, which basically means if we start with the answer, how do we determine what did we start with? So we're going to say that each of these problems is a y equals, and we're going to say that each of these y equals is f of g. So we're going to say that u is equal to g of x, and that's always going to be the inner function, where y is equal to f of u, and that's always going to be the outer function. So for each of these four problems, before I even take any derivatives, I just want to make sure that I can determine who's the inner function versus who's the outer function. So the inner function means the function that you started with. So here in the first row, to me, that looks like x plus 1. What function would you be putting that into? And again, sorry, that should be u equals. So u equals x plus 1. Then, in order to get the answer, you would have to put the x plus 1 into some function, which in this case would be 1 over u. How about the sine of 2x? Well, if you try to identify the innermost function, to me, I think that you're starting with a 2x. Where are you putting the 2x into? You're putting it into a sine function. How about the square root of this trinomial? Well, to me, I think I'm going to start with the trinomial, which would mean that I have to end with a square root function, or of course, you could say to the 1/2 power. And then for the last one, please be careful. When I say to you y equals the tangent squared of x, what I'm really saying is the tangent of x, the whole thing squared. If you think of it that way, I think it's easy to see that the tangent is the inner function, which means the outer function has to be the squared. And again, I tried to kind of help you set you up here. who should be the u equals and who should be the y equals. So again, the y equals should always be the outside function, and then the u equals should always be the inside function. So part of your homework tonight is just going to make sure that you understand who's the inside and who's the outside. To be honest, it's really not that hard to do for today's lesson, but instead of having 2 things in a row, we're eventually going to have 3 or 4 things in a row with trig and all kinds of stuff, and then it becomes more and more important that you can do this. So I think we went ahead and set ourselves up for success. So let's go ahead and do some examples. So find the derivative. And again, from this point forward, as long as it's a y equals, I do want you to call it dy dx using the chain rule. So y equals 3x squared plus 1 cubed. We're going to take the derivative, which again, I'm telling you to call dy dx. You're going to bring down the 3, take the entire quantity to the 1 less power. And now, according to the chain rule, you're going to take the derivative of the inside. So the derivative of x squared, 2x. The derivative of a constant is 0. In order to get your final answer, all you're going to do is clean up a little bit. So dy dx, 3 times 2x is going to give you 6x times x squared plus 1 squared. And it turns out that is as far as I want you to go. I don't want you to FOIL it. I don't want you to multiply it out. Eventually, we're going to set that equal to 0 and solve for stuff. So it's much better to have it factored as opposed to multiplying it out. Very similar over here in the second example. Notice we have a slightly messier exponent, but the same rule applies. Bring down the 5/2. Take the entire quantity to the 1 less power. So 5/2 minus 2/2 would be 3/2. And then take the derivative of the inside. The derivative of x cubed would be 3x squared. The derivative of a constant is 0. Clean it up. So 5 over 2 times 3x squared. That would give you 15 over 2 x squared times x cubed plus 3 to the 3/2. And we wouldn't care whether you left it as a 3/2 or the square root cubed. Anything would be fine so long as your exponents are positive. So maybe you're thinking, okay, that was an awful lot of work and words leading us up to this. It seems pretty easy. And the truth is it is, at least for today. So let's go ahead and try a few more. Before we do that, just a reminder here. So this is a reminder of the general power rule. Of course, that means if you're taking the derivative of something to an exponent, you would move the exponent to the front. You would then take the power to the 1 less. And now don't forget to multiply by the derivative of the inside. And the derivative of u, you can also write as u prime. So let's see how that would look in action. So again, take the derivative using the chain rule. So dy dx. I'm going to move down the 3 times 2 is 6. I'm going to take the entire quantity to the 1 less power times the derivative of the inside. So the derivative of negative 3x to the 5th would be negative 15x to the 4th. The derivative of a constant is 0. When you go to clean it up, so 6 times negative 15, that's negative 90, x to the 4th. Negative 3x to the 5th plus 1 squared. And again, no reason to multiply out anything or try to solve anything. We're not quite there yet. For the next one, you want to be especially cautious because you have a negative exponent. If you have a negative exponent, you just want to make sure you're doing 1 less. So negative 2 to the front, negative x to the 4th minus 3. Make sure you go to the 1 less power, and 1 less than negative 2 is negative 3. You then have to do the chain rule. The derivative of negative x to the 4th would be negative 4x cubed. The derivative of a constant is 0. When we go to clean it up, I want to do 2 different things. So I'm going to multiply negative 2 times negative 4x cubed, which is positive 8x cubed. And then I do not want any negative exponents in my answer. So I'm going to take this negative x to the 4th minus 3. I'm going to move it into the denominator, which will make it to the 3rd power. Now, again, if there comes a time when you can factor, simplify, and reduce, you should, but we're not going to hit that time yet. So for now, just make sure that you multiply anything that's on the outside and make sure that you don't have any negative exponents. Just a couple more. So here, find the derivative, again, using the chain rule. That's the directions for almost everything tonight. Notice that instead of being a y equals, it's a g of t equals. So obviously continue to call this g prime, since the dy dx notation doesn't make sense. Before I can even think about using the chain rule, I have to go ahead and do a rewrite step, which means I have to remember that this is to the first power. So I'm going to rewrite this as -7 times 2t minus 3 to the -1. The derivative of g of t is g prime of t. I'm going to multiply the -1 times the -7. That's a +7. I'm going to take the entire power to the 1 less. 1 less than -1 is -2 times the derivative of 2t. For my final answer, 2 times 7 is 14. Move the 2t minus 3 to the bottom. Don't forget to square it. And that, of course, will make it into a positive exponent. And our last problem of the day, find the derivative using the chain rule. So this is the cube root of something being squared. So hopefully you remember that a cube root is really equivalent to a 1/3 power. If you're talking about something being squared, being raised to the 1/3 power, then the first thing I'm going to do is rewrite this as x squared minus 1, the whole thing to the 2/3 power. Remember, 2 squared raised to a third, you would multiply those exponents. So 2 times a third would give you 2/3. Remember, the rewrite step is often the most important, which is what that was. And now go ahead and take the derivative. We have to call this f prime since dy dx wouldn't make sense. Bring down your 2/3. X squared minus 1 to the 1 less power. So 1 less would be minus 3/3. That would then give us the -1/3 power times the derivative of the inside, which would be 2x. So in my final answer, I have a 2 up top and I have a 3 down low. So the 3 is going to go to the bottom. I'm going to multiply 2 times 2x to get 4x. Then I'm going to bring the x squared minus 1 to the bottom, which would make it the positive 1/3. That's a perfectly fine answer. You could also write it as 4x over 3 times the cube root of x squared minus 1. And guess what? Both of those are going to be perfectly acceptable answers. So that's your very first day of the chain rule. Just a note about the homework, you'd be surprised how many years we go over the homework the next day and almost everybody has only half the answers. And they're like, well, where are you getting that second value? The answer every single time is the chain rule. Don't forget to take the derivative of the inside. So other than a couple problems that ask you to set up the f and the g like we did along the way, they all want you to take the derivative. And again, please be careful to use dy over dx notation when possible. So thanks very much, guys, for tuning in, and we will catch you next time.